So just a 2-minute reminder about what Fourier series are, what we've seen so far. So a Fourier series takes the form of what's shown in equation 3.1 there on the screen. It is a way of expressing a function f which has certain properties. We're talking about periodic functions on the interval minus pi to pi, and satisfying some other well-behaved properties. The function can't be too strange. You only have a finite number of discontinuities on that interval, the finite number of minimums and maximums on that interval. But that's most everyday functions. So Fourier series for a function like this f, it's a way of expressing it as a linear combination of certain basis functions. The set of all these functions defined on the interval, it naturally has the structure of a vector space. So you can add functions together and you can take scalar multiples of functions. It's an infinite dimensional vector space. Okay? So the basis for it, the way we've set it up, the basis for it consists of the constant function, all of these cosine functions for every n bigger than 1, and all of these sine functions, sine of n times x. So what you're looking at there in equation 3.1, you can consider that as a vector written as a linear combination of basis vectors. Except in this context, it's our function, f of x, expressed as a linear combination, an infinite linear combination of the constant function, this collection of cosine functions for each n, and the collection of sine functions for each n. So what we're going to see today is some examples of finding these for some example functions f. So the task there is to identify what the coefficients in this linear combination are. So to find the Fourier series for a given function f, that's the problem of finding a naught, finding all the an's, and finding all the bn's. Now where do these come from? We discussed this last time. We have the Fourier series, the Fourier coefficient formulae. These are these ones showing on the screen, 3.7 through 3.9. These are formulae that tell you how to express the constant function, the constant coefficient a naught, the an's and the bn's, and they're all expressed as integrals of f multiplied by the corresponding basis function. Another way of looking at these integrals, which we discussed last time, is these are inner products. The coefficient is a scaled version, so that's the 1 over pi is a scaling factor, but the coefficient is essentially the inner product of the function you're dealing with the basis function. Okay, so the constant function is the inner product of the function f with the constant function 1, so it's just the integral of f over the interval. The coefficient an for a given n is the inner product of f with the cosine function for that same value n. Okay, and the inner product, the standard inner product we're using, the inner product of a pair of functions from this vector space, is you integrate the product of the two functions across the interval. Okay. Now the example we showed you first time, so here is an actual function. Think of this as the Heaviside step function on the interval of minus pi to pi. It's shown here in red. So it's 0 on the first half of the interval, then 1 on the second half of the interval. This slider is m. So this m is the number of terms. See the Fourier series formula again here in example 3.3. Okay, you get exact equality when you take the infinite sum. If you just take a finite partial sum, some collection of initial terms of these two infinite sums, then you get an approximation to the function. So what you're seeing here at the moment, the Fourier series, see I've got m, the slider there, set to 0. So the only term I'm using there is the constant term. So for this square wave function, it's also called, the constant term is just the average value of the function. So the average value of the red function is of course a half. Half the time it's 0, the other half the time it's 1, so its average value is a half. So that's the best way to approximate that function, just using a constant half. And then as you increase the number of terms, we gradually bring in our sine and cosine functions. Now for this particular function, it actually turns out they only consist of sine functions. We're going to see that for ourselves. We're going to derive that result for ourselves. So this here is what the Fourier series looks like for the square wave function. And we're setting different values of m, the upper bound and the sum, using this slider here. Okay, so when we've got m equals 1, we've got the constant term, a half, and one of these sine functions, sine of x, a certain multiple of sine of x. And as you increase m, get more and more sine functions in, your blue Fourier series, or the partial Fourier series, is better and better approximating the red function. Go up to 6 terms, you now got pretty good approximation to it. Bump it up to 15 or something, you should get a very, very good approximation to it. Okay. So most of the time here, I don't know if I'm getting 2 graphs there, most of the time there, the Fourier series is very close to the function. It has to deviate away from the function a little bit when it gets close to the points of discontinuity. That's a natural phenomenon which we'll discuss soon enough. Okay, so this is just kind of looking at here how, as you increase the number of terms in the Fourier series better and better approximates function. This wobbling here at the points of discontinuity, this is a name, this is called Gibbs phenomenon. You see, the red function, the objective function f is discontinuous here, but we're approximating it using a continuous function, a linear combination of sine functions. Now, the sine functions are all continuous. So the Fourier series itself is continuous, but you're kind of forcing a continuous function to act like it's discontinuous. That's quite an ask. So before it makes this sudden jump in value, it has to wobble around a bit. This has been likened to, if you're riding a bicycle. If you're riding a bike, you'll be familiar with this. If you're riding a bike very fast, if you're coming up to a 90-degree turn, the next time you do that, if you try and be mindful of what you're doing, you don't just cycle in a straight line and suddenly, immediately turn in the direction you want to go. If you're going very fast, if you're a good cyclist, if you look at what you do, when you're coming up to the turn, before you make the harsh, severe turn, you sometimes wobble a bit in the other direction. You kind of round out the corner and then go. If you want to turn very fast to the right, you're cycling up to it, you very often wobble left a bit and then go into the right turn. Okay? Try doing that the next time you're cycling fast. In a sense, this is what the Fourier series function is doing. See, it's chugging along here, happily wobbling around 0, but then we're asking it to suddenly jump up to the value 1. And it has to kind of prepare for that a little bit, and then boom, it goes up to 1, and it continues on. We'll consider that phenomenon in a bit more detail later on. So that's characteristic of how Fourier series act near points of discontinuity. And it doesn't matter how many terms if I bump it up to 50, it's still present. So when you've got 50 terms, essentially you've got, high degree of accuracy over most of the interval, but still at the point of discontinuity, you've still got a bit of deviation happening. Okay? And you can't get rid of that deviation. You can squash it closer, you can concentrate it in a kind of narrower interval around the point of discontinuity, but you can't get rid of it by just taking some finite part of the infinite Fourier series. Okay, so that's a quick recap. So what we'd like to do now, work through this example, is actually derive this Fourier series for ourselves. Okay, so this is, I think it's set here as an exercise. Yeah, this example 3.4 here. So we're going to apply the coefficient formulae to derive this Fourier series for this function. Capture this on the there. Okay, so our function f, the square wave function, it takes 2 values, 0 and 1. 0 if you're on the negative half of the interval, and 1 if you're on the positive half here. what you do exactly at the point 0 isn't really that important. But for the purposes of this example, so at x equal to 0, we're taking the value 1. But it wouldn't change things if you made it take the value 0 at 0. That's not important. Okay, so we want to use the coefficient formulae. To obtain constant coefficient A0, or twice the constant coefficient. The constant coefficient appears as half A0 in the Fourier series. The ANs and the BNs for n bigger than or equal to 1. Okay, so we'll just dive in straight away and start doing this. So the formula for A0 is 1 over pi times the integral from minus pi to pi of the objective function f dx. So this integral is the inner product of the function f with the constant function 1. Now, what is that? Well, you see, the function f is pretty simple. It's either 0 or 1. 0 on the first half of the integral and 1 on the second one. So really, we're just integrating from 0 to pi dx. Right? So that's just bringing in the definition of f. And the integral from, sorry, I'm just integrating 1 dx. The integral from 0, the integral of the function 1 over a finite interval is just the length of the interval, pi. So this A0 just comes out as 1. That's your A0. Okay, so that explains why, but remember, A0 appears, the constant coefficient in the Fourier series is half of A0. Formula. So that confirms that we've got that half value, the constant value in the Fourier series. So we expected that, as expected. Then we want to let n be some number bigger than 1, and we want to look at the other ends. And we should be able to work them all out in one go, rather than work out A1, then A2, then A3. Should just be able to deal with them all at once. So it's equal from minus pi to pi of our function f of x times the cosine of nx dx. So this may or may not be a hard integral to work out. So you substitute in the definition of the function f. Remember, f is just 0 on the first half and 1 on the second half. So this reduces to just 1 over pi times the integral from 0 to pi cosine nx dx. So integrating cosine isn't too hard. It's sine of nx over n, evaluated at minus pi and pi. But what is that? Well, that's just 0, because to do the evaluation of the limits, you're working out sine at an integer multiple of pi. But when you evaluate the sine function at any integer multiple of pi, you always get 0. So evaluating this square bracket here, you're just doing 0 minus 0. So it's just 0. So it's just 0. All the ANs are equal to 0. For every n bigger than 1. And this is as expected as well. As expected meaning comparing with the given Fourier series. The answer, the one we were looking at in the demo. Is that okay? Any questions or clarification you'd like on that? Okay. So this means if the ANs are all 0, it means there aren't any cosine functions in the Fourier series. The coefficient of them all is 0. That confirms with the fact that the answer we're going for doesn't feature any cosine functions. It only features the sine functions. Okay, that's good. So now we let n bigger than or equal to 1, and we go for working out the bn's. This is 1 over pi, the integral from minus pi to pi, f of x times sine of nx dx. And again, because of the nature of f is 0 on the first half of the integral and 1 on the second half, this becomes the integral 0 to pi times sine of nx dx. Excuse me, sorry? That's 1 over, sorry, 1 over pi. Line pi, yeah. Well, the integral of 1 over pi, sorry, of sine is straightforward enough. It's minus cosine of nx over n. And this gets evaluated at 0 and pi. So we've got 1 over pi. Well, when you evaluate this, let's bring the n outside as well. 1 over n pi. And we've got minus the cosine of n times pi minus what we get when we evaluate the cosine at 0. The cosine at 0 is just 1. So what is it? It's minus minus 2, so it's plus 1. Now, what kind of value is that? Well, it's something plus 1 in the bracket. What's something is cosine of an integer multiple of pi. So you think of your unit circle in the complex plane, integer multiples of pi, you've either got a cosine value of plus or minus 1. So this thing here, this first term in the bracket is going to alternate between plus and minus 1. So it's going to alternatively knock out the 1, cancel out to 0, or come to 2. So that value in the round bracket is going to alternate between 0 and 2. So we've got this minus sign there, so we just need to work it out. It's going to be based on whether n is even or n is odd. When n is even, the cosine of an even multiple of pi is plus 1. So when n is even, yeah, you've got a minus 1 and a plus 1. So it just comes to 0. But when n is odd, cosine of an odd multiple of pi is minus 1. The additional minus sign makes it plus 1. You got plus 1 plus 1, so you got 2. It becomes 2 over n pi whenever n is odd. When you're deriving Fourier series for kind of some standard functions, some simple functions, you quite often come up against this kind of behavior where the coefficients split based on either the parity of the index, whether the index is even odd, or sometimes what the index is modulo 3 or modulo 4. Sometimes it splits into some different cases. Any questions on that derivation there? Okay, so we've got all the ingredients for the Fourier series now. We've got our constant coefficient A0. We've identified that all the ANs are 0, and half the BNs are 0, and half of them aren't. So you've got all the ingredients there. We just need to put it together then. Put it together and form the Fourier series. Okay. We can now form the Fourier series for the square wave function f. As f of x, well, it's a half of A0, but there aren't any cosines. There's no cosines, since an is equal to 0, for n bigger than or equal to 1. So it just looks like this, and now let's actually put in the values. A0 was 1, so this initial constant is a half. And then, so which, you see, half of the n's are 0. So we only want to capture the odd indices n. So in order to capture the odd indices n, we can make n go from 1 to infinity, and just refer to b of 2m minus 1. See, as m runs through all of the integers, 2m minus 1 runs through all of the odd integers. 1, 3, 5, 7. So this is a half plus sum from m equals 1 to infinity. This is 2 over 2m minus 1 times pi times the sine of 2m minus 1 times x. So maybe some of that you can bring outside the summation to simplify it a little bit. Yeah, the 2 over pi you can bring outside. There are constants. 2 over pi times the sum, m equals 1 to infinity, and then this is multiplied by 1 over 2m minus 1 times the sine of 2m minus 1. So that, I think, is exactly what's shown. Yeah. The solution in the notes. Except I've used m for the index there in the notes at the end. So this is the formulae. Well, this is the infinite sum in the computer demo I was showing you earlier on Sage Cloud. We were looking at the initial partial sums of this for increasing values of the top limit. Any questions about that, or things I could clarify about that? And we will do another example here. Shortly we'll go on and do the example for the function f of x equals x, the linear function. But there's a very sweet, interesting result we can get out of this. See, this is in example 3.5, and it's because we've got a pi knocking around here. We've got a pi knocking around, and we've got infinite sum of these fractions. There's an interesting result we can extract out. Because what we've got here is an equation, the Fourier series for this function. So how about we evaluate this? See, okay, we've got these sine functions here, but if I evaluate, there are some nice values floating around. Yeah, I'm doing sine at an odd integer multiple of x. If I put in a nice, well-chosen value for x there, these sines, I'll be able to understand them quite well. We put in the value pi over 2. How about we evaluate this at pi over 2? So on the left-hand side, you've got f of pi over 2, which by definition is 1. Yeah. Square wave function, heavy-side step function, pi over 2, simply 1. But let's look at the Fourier series. Well, the Fourier series is a half. It's 2 over pi. Can I do this in my head? Yeah. Let's try and do it in my head. Your head. So we're putting in pi over 2. So our sines are going to be sine of an odd multiple of pi over 2. What does sine of an odd multiple of pi over 2 look like? Well, that's either 90 degrees pointing straight up on the unit circle, or 270 degrees pointing straight down on the unit circle. So those sine values are either plus or minus 1. So as you go through the odd multiples of pi over 2, sine of an integer multiple of the odd multiple of pi over 2 is going through the values plus 1 and minus 1. So we're over 2m minus 1, and we just need the alternating positive and negative sign. You just have to start it in the correct place. So when m equals 1, we're looking at sine of pi over 2, which is plus 1. When n equals 2, we got a sine of 3 pi over 2, which is minus 1. So it begins plus 1 with m equals 1. So to get that behavior, we have minus 1 to the power m plus 1. It's an alternating positive and negative sign, but it begins positive at m equals 1. So what does this say? This tells us that this half here we can bring over the other side. A half is equal to 2 pi. So this is a nice, okay, you get a clearer idea of this sum if you just write it out. It's the sum, it's the alternating sum of the reciprocals of the odd integers, beginning with a positive sign. So it's 1 minus a third plus a fifth minus 1/7 plus a 9. So the alternating sum reciprocals the odd integers. I think maths is all about symbols and signs, but you can do maths in language. You can do maths without any symbols as well. Alternating sum of the reciprocals of the odd integers, beginning with plus 1. You have to say if you're beginning with positive or negative. And you know, pi is this very important constant, this constant from the circle, the ratio of the, whatever it is, circumference to the diameter of the circle. Very important number, the foundation of a lot of geometry and so on. But here we've got, you know, a disturbingly simple formula for it. It says, you rearrange this, it says that pi is 4 times this sum. Pi is 4 times this alternating sum of the reciprocals of the odd integers. So really nice result. If you haven't seen it before, it's kind of quite a surprising result in some ways. There's nothing obviously. See, pi, you think of pi as something naturally associated to the circle, but it's hard to see where the circle is in the sum of the reciprocals of the odd integers. So it's kind of, you know, I find it very. I find this formula quite surprising. We might just want to try and numerically verify it. Something weird's gone up, like with the graphs there. Let's just verify it, make sure it makes sense. So we can try, we'll set a pi estimate to be the sum. So what's this quantity? It's 4 times minus 1 to the power x plus 1 divided by 2 times x minus 1. The sum of that for x in the range beginning at 1 and ending at some upper limit m. I better set m equal to something. So let's say m equals 5. Oh, 304. So we do so we'll get a fractional form and the number form. So if you take 5 terms, if you just go up as far, well, 5 would go up as far as the 5th odd number, so 1 over 9. So I think this is the value of this sum here. Although it's only going up as far as the 4th. No, if I make m equals 6, this range thing only goes up as far as m minus 1. So if I make range go up to 6. So 3.339 is the value of this expression there that's on the board. If you just go up as far as 1 over 9. But if you increase the upper limit, I mean 3.339 is already quite close to pi. So the big long string there is actually a fraction. There's the division sign over here. So this huge integer over that huge integer. But you see we're getting very close to pi now, 3.15. Up to 1,000 terms in that sum. So you get some gigantic fraction. Well, it is 3.14259. Okay, so it does check out. It does seem to verify. Okay, so that's a nice little result which falls out of some of these Fourier series. There are a whole bunch of interesting infinite series representations for pi. And look them up. There's a whole large family of various varying complexity of infinite series representations for pi. All right, so let's look at another example. This isn't kind of declared in the notes as such, but we'll just do it ourselves. We'll find the Fourier series for the function f of x equals x. Okay, this is our standard linear function. Get this on the recording as well. Okay, so we're looking for a representation for x as an infinite sum of sines and cosines. Okay, so let's see if we can do this. So we do this as before. First we look for a naught. So it's 1 over pi times the integral from minus pi to pi of x dx. We integrate the function over the integral. Well, that's a pretty straightforward integral, isn't it? X squared over 2, evaluated at pi and minus pi. But of course, when you evaluate x squared, pi, evaluated at minus pi, you get the same result, pi squared over 2. But you have to subtract, when you evaluate after the integral, subtract the upper evaluation from the subtract the lower evaluation from the upper evaluation. So this is just going to give you 0. So the constant term in this Fourier series is 0. That makes sense, doesn't it? What's the average behavior of x across the integral minus pi to pi? 0 is the average behavior. The line, the 45-degree line going through 0, and you're on an interval centered at 0, so the average behavior is 0. So this, which agrees with average behavior of f of x equals x across the integral minus pi to pi. So we're pretty confident in that result. Now we go for the ANs. Okay, so by definition, by the coefficient formula, this is integral minus pi to pi of x times the cosine function nx dx. Now, how do you integrate x times x times cosine function? Well, you can either just remember what it is, use the standard result, or you normally think of that as integration by parts. You've got a product of two functions of x, and one of them will kind of disappear or simplify to a constant after you differentiate it. It's possible to express the other one as a derivative. So, there's integration by parts for this. So integration by all your standard techniques of integration, you kind of need to have ready and waiting to do these. So integrating this by parts, so we think of the cosine function as the derivative of sine of nx over n. We need to multiply that by x, so that's one product of these two evaluated at minus pi and pi is one part. Then we subtract the integral from minus pi to pi of this representation sine of nx over n, and that gets multiplied by the derivative of the other factor x. Derivative of x down to x is just 1, so I have an extra factor of 1 in there, which I'm not going to bother to write down. So that's the integration by parts. Now, what's going on here? What do you get from evaluating this first bracket? You're looking at sine. See, one of the factors in there is sine of an integer multiple of pi, plus or minus pi. But sine at any integer multiple of pi is 0. So what you get in here is just 0 minus 0, so you get 0. So this thing just goes to 0. This thing we got to do the integral, so sine integrates to minus cosine, so that'll cancel that minus sign there. So the cosine of nx, you need another 1 over n, so it's now over n squared. And this gets evaluated at pi minus pi. It's normal after the integral. Now there you're looking at cosine of an integer multiple of pi versus cosine at an integer multiple of minus pi. Those are always going to be the same value. See, cosine of any a is always equal to cosine of minus a. Cosine is a symmetric function, an even function is the technical term for it. So here we're just subtracting either plus 1 from itself or minus 1 from itself. So again, you get 0. So you get, hey ho, big, uninteresting 0. Well, it's not uninteresting. So there are no cosine functions in the Fourier series for this function f of x. There's no constant and there's no cosine function. So there better be some sine function. Okay. So all of the representation of this function f of x equals x is all piled onto the sine function. No constant term, there's no cosine functions. Everybody clear on the integration there? Any clarification I could provide? Okay. So we go into the bn's, and we'll be hoping to find something non-zero here, where we have to find something non-zero. And it's going to be integration by parts again, isn't it? Taking the inner product of our objective function x with sine of nx, with the coefficient bn. So integration by parts is before the 1 over pi times x, and the representation now is minus cosine nx over n. Derivative of that, which gives you sine of nx. So you have this evaluation, and then you've got minus the integral from minus pi to pi. We're integrating minus cosine, so this is going to be a plus cosine nx over n dx, and that's multiplied by the derivative of x, which is just 1, so take that integral. Okay, again, yeah, no. So, okay, you just have to proceed very carefully. Very often these things, there's minus signs flying everywhere. You're evaluating things at edges of integrals. So you just got to proceed carefully. See, if you look what's going to happen to this integral is going to go to sine nx over n squared, evaluated at minus pi and pi, but that's going to be equal to 0. So the second integral part just gives you 0. Okay? Because again, you're evaluating sine of nx at pi and minus pi. So something non-zero comes from this evaluation here. Indeed it does. You've got 1 over pi. Let's bring the n out to the front, just not to be confusing things in there. very carefully here, you've got minus pi times the cosine of n pi minus, now you're putting in minus pi for x. You put in minus pi for x here, it becomes plus pi. And then you've got cosine at minus n pi. Yeah, you've got to keep track, careful accounting of minus signs here. And this factor of pi, well, that factor of pi will cancel out with this pi here. It'll just be left with 1 over n. And let's take that, 1 over n minus the cosine of n pi minus the cosine of n pi again. Remember, cosine of a is always equal to cosine of minus a. So this minus sign here just evaporates. Okay? Cosine always agrees on plus and minus at the same absolute value. Okay? So that minus sign there just disappears in a puff, and all the other minus signs remain. So what you're left with is minus 2 over n times the cosine of n pi. Now we'll finally fully evaluate it. What is cosine of n pi? Cosine of an integer multiple of pi. That alternates between plus and minus 1. Okay? Plus the cosine of n pi is plus 1 for even n, minus 1 for odd n. Well, you've got this extra minus sign here. So what we get is the bn is either 2 over n or minus 2 over n. And it's 2 over n for when n is odd, and minus 2 over n when n is even. Does that make sense? So we've got all the ingredients for the Fourier series. So our Fourier series for f of x equals x is this x. And there's no constant term, there's no sine, there's no cosine terms. So it's just a big sum of sine terms. So it's bm times the sine of mx. So that's true since an is equal to 0 for n greater than or equal to 0. It's what we found above. And bn is 2 over n, 2 over m. And that has a positive sign, which is a positive negative sign. It's positive for n odd, negative for n even. So if we make this m plus 1, squash there, sorry, and sine of mx. Or you can take the 2 outside. It's 2 times sum from m equals 1 to infinity minus 1 to the m plus 1 over n multiplied by sine of mx. Okay, so this is the Fourier series for function x. Now, can we verify that? Yeah, we can try and if we look back at this computer demo we had here, I think we can alter the code here. See that this little function here, I'll just quickly alter the code. This little function here returns the coefficient, which is minus 1 to the power m plus 1 times 2 over m times sine of m times x. And if we take out the constant term of a half, and then here plot the comparison function x from minus pi. Erase all this because that's talking about the other function. So I think I've made the necessary changes there to this code to, yeah. So there, when we've got n equals 0, so when we're not taking any terms of the sum, we've just got the constant 0. So there's our objective function, f of x equals x, and the Fourier series is just identically 0. When you go to one term, then you've got the first sine function. That's the sine function, which is the best one that approximates the function f of x equals x. As you keep on increasing the number of terms in this sum here, you get better and better approximation to the function x. So if you bump it up to a huge number, you see very good agreement. And again, remember, the objective function we're dealing with here is the function f of x equals x, but considered to be periodic to pi. This is sometimes called the sawtooth function. So how the red graph would continue on would be on the next interval from pi up to 3 pi, it would just be the repeat of this. So it's like a sawtooth pattern. So we've got points of discontinuity at either end of the interval. And so that's why we again see this Gibbs phenomena, which we can't get rid of, which is where you've got good agreement on the interior of the interval, but as you get close to the point of discontinuity, the Fourier series has to deviate a bit before it makes the sudden, nearly discontinuous change in value to get back down to -1. Okay, that's good. We got through some good examples there. So we'll do some work with these in the tutorials and continue on the theory next week.